Okay, this is probability review video part 1, and this is covering basic probability and expected values. Remember real quickly, all probabilities must be between 0 and 1 inclusive, and to be a valid probability distribution, the probabilities must sum to 1. So here's our first scenario. A sporting goods store announces a wheel of savings sale. Customers select the merchandise they want to purchase. Then at the cash register, they spin a wheel to determine the size of the discount they will receive. The wheel is divided into 12 sections. Like a clock, 6 of those regions are red and award 10%. So basically 6 out of 12. Now I could list this as a decimal, but I'm just going to list it as a fraction. The 3 white regions award a 20% discount. We have 3 at 20%, 3 out of 12 or 25%. And 2 blue regions, 40%, so 2 out of 12 or 1/6. And then we have 1 out of 12 that's paying out 100%. Excuse me, 1 out of 12. And if I were to sum those up, 6 plus 3 is 9, plus 2 is 11. So that's 12 out of 12 or 100%. And that right there tells me that that sums up to a valid probability distribution. And these probabilities are between 0 and 1 with no negative probability. So it's a valid probability distribution. What is the expected size discount for a given customer? So expected value has the formula or each individual X times the associated probability. So in this case, we're going to basically be going, and you have to show your work on these. You can't just plug it into the calculator. Now, the fact of the matter is I am going to plug it in the calculator in just a moment, but right now you're going to have to show your work, and then we can use the calculator. So my X was 10, so 10 times 6 over 12. And if you had wanted to, you could have used 1/2 plus 20 times 3 over 12 plus 40 times 2 over 12 plus 100 times 1 over 12. All right, so here's what I'm going to do. I'm going to go ahead and plug this stuff in the calculator. I'm going to go to Stat Edit. And yes, I could have done this by hand, but I've basically gone 10, 20, 40, and 100. And so this was 6 out of 12. And by the way, here's a shortcut way to do that. I'm going to clear that. 6, enter, 3, enter, 2, enter. And the last one was a 1. And then I just went all the way up to the top and I went second 2 for L2 divided by 12. And there you go. So it gives me the actual probability. So now I'm going to go stat, calc, one variable statistics. My list is an L1. My frequency is an L2. And sure enough, I get my X bar equaling to 25. So what I'm expecting here is I'm expecting a 25% discount. That's my answer. And so we would need to write, we would, on average, we would expect a 25% discount. All right. And that's the way you would write it out. Now, the next one asks for the standard deviation. Well, the standard deviation has the individual X's minus the mean times the probability. Of course, it's squared and it's under the radical. I'm going to go ahead and draw a giant radical out here just because I can fit everything underneath it at the end and it just makes my life easier. So my first X was 10 minus, we expected a 25 squared times the probability. Well, we already know that's 6 over 12. And again, I could have used the decimal. And I can do the plus dot, 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 but for here, I'm not going to. I'm just going to show every single one of them. Plus 20 minus 25 squared times 3 over 12 plus 40 minus 25 squared times 2 over 12 plus 100 minus 25 squared times 1 over 12. The calculator automatically did the work for me already. So I just went back and there it is. On average, now it just happens these end up being the same. Don't expect that. That's just the way it worked out for this one. So the standard deviation in this case is 25. Okay. So what is the probability that two customers in a row get only 10%? Whenever they ask for problems like this, I actually fill in two blanks. It's like, oh, I'm doing two things. And so I need a 10% and a 10%. So the probability of getting 10%, we just said, was 6/12. And by the way, that reduces to 1/2. So I'm going to go ahead and reduce that to 1/2. So 1/2 and 1/2. So in this particular case, 1/2 times 1/2 equals 1/4. Now, if you didn't reduce it, you'll still get there. Just the numbers get a little bit bigger. What's the probability at 3%, 3 consecutive customers get 20% discounts? So in this case, I have 3 blanks because I'm doing 3 things. So we're looking for a 20% discount. Well, 3 out of 12 is 25%. So that's basically 1/4. And I could use decimals and it still work just as well. I could have done 0.25 times 0.25, etc. And I would get there. Hold on for just a moment. The screen is sending me messages that I really rather not see about rebooting the computer. That's always a good sign. So in this case, I'll get 20%. And so we're going to basically go, okay, 0.25 or 1/4. And I need 3 of them, so carry it to the third power. And so I end up getting 0.015625. And by the way, you can round or truncate at the 4th decimal place, but here I'm going to go ahead and just take it all the way out. So that's the probability. What's the probability that the first gold winner is the 5th winner in line? All right, so the first gold winner, well, that means that's 1 out of 12. All right, so how many spaces? Well, that's 5. So 1, 2, 3, 4, 5. And essentially, this is not gold, not gold, not gold, not gold, and this is a gold. Well, the probability that these gold is 1 out of 12. Well, not gold is going to be 1 minus 1 out of 12. So I could write 1 minus 1 out of 12, but that's basically just going to be 11/12 times 11/12 times 11/12. Now, this is actually a geometric, but we will get into that in the next, well, not this set of videos, but in the next section. So this is basically, I could have written it if I wanted to, just and it'd be absolutely correct to go 11/12 to the 4th power times 1/12. I just find that if I start off this way, I don't make a careless error. So in this case, 11 divided by 1/2. I'm going to raise that to the 4th power times 1 divided by 12. And I end up getting 0.05883. Hope I wrote that down correctly. Wouldn't be the first time I made careless errors. And if you've seen the videos, you know that I do that. All right. What's the probability that none of the first customer gets a discount over 20%? Well, first off, none, that would mean, and then we have 4 customers, so let's go ahead and make our 4 blanks. So none getting over that would mean that, hey, in this case, we're looking at 6/12 and 3/12, which is 9/12. So this is essentially saying that 9/12, because they can get up to it, but they can't include it. And in other words, and I could have just made this, and it probably made it a lot easier if I would have just gone 3/4 to the 4th power. So 0.75 or 3, let me clear my calculator up, 0.75 raised to the 4th power. and we end up getting 0.3164, etc. 0.3164, and I'm just going to truncate. Finally, what's the probability that there's at least one gold customer among the first? As soon as we work with this least bit, we kind of have an issue. We are basically going to need to use the complement. And I know it said use the complement here, but because of the type of problem it is, we could get by with it. We will see one where we have to, but here we're going to have to use the complement. So what's the probability that there's at least one gold winner? So with at least one gold winner, that means if I have 6 customers, I could have 0 gold winners, 1 gold winner, 2, 3, 4, 5, or 6. They said at least one. So this is what I'm interested in, because I'd have to figure out multiple probabilities, the probability of 1, the probability of 2, the probability of 3. It'd probably be a lot easier for me to go 1 minus the probability of getting no gold winners. Okay, well, I'm gonna have to pause this video. My dogs are barking and it's 2 o'clock or 2:30 in the morning. Okay, so anyway, what's the probability that there are at least one gold winner among the first 6? So that's 1 minus, and we said we're going to do the probability of 0. So 1, 2, 3, 4, 5, 6. Now, the probability of 0 is basically everyone not getting a gold, so not gold. All of these are going to be not gold. So in this case, the probability of not gold was 11 out of 12, because the probability of gold was 1/12. So essentially, we're going with 1 minus 11/12 raised to the 6th power. So let's calculate that out. One minus parenthesis 11 divided by 1, 2, close parenthesis, raised to the 6th power. And we end up getting 0.4067. All right. All right, so moving on to the next part of this. A city water system involves 3 pumps, the failure of any one of which crashes the system. So basically, when they do this, of any one, that's like saying if one, or saying at least one. So this is essentially a hidden way of saying at least, which crashes the system. The probability of failures for each pump are 0.025, 0.034, and 0.02, respectively. Assuming the pumps operate independently, and we need to know that because if they're independent, we can multiply. What's the probability the system does crash? Well, at least, remember, at least is that keyword for doing a 1 minus. So I need to know if this one crashes, it crashes. If this crashes, it crashes. If any combination of 1, 2, or 3 crashes, it crashes. So I need to do the at least, which is the complement, which is the 1 minus scenario. So I'm going to be working with the probability of it not crashing. So 1 minus not crash, and not crash. So what's the probability the first one doesn't crash? Well, that's going to be 1 minus 0.025. Now I'm just going to do 1 minus 0.025 is 0.975. So this is 0.975. I'm going to put that in parentheses. And then 1 minus 0.034. That's going to be 0.966. and 1 minus 0.02, which is 0.98. So once again, I'm working with the complement because I can have 0 crash, 1 crash, 2 crash, or 3 crash. If at least 1 crashes, the system crashes. So this is why I want to work with 1 minus the probability that none crash. So in this case, we're going to be going 1 minus parenthesis 975 times 0.966 times 0.98, close parenthesis. And this is going to be 0.0769. And all I did was truncate. All right. So as we continue on, a city water system involves 3 pumps, the failure of any one of which crashes the system. So once again, we're working with that same if one or at least one. The probabilities of failure for each pump are the same. Assuming that the pumps operate independently, what is the probability that the system does not crash? Well, that one's easy because basically we're looking for 1, 2, 3, not crash, not crash, and not crash. Oh, well, we already did that. So in this case, 0.975 times 0.966 times 0.98. And we end up getting 0.0923. And some of you are going, hey, you know what? We could have just subtracted that from 1 and that would have worked. And the answer is yes, it would have. But I want to show you if we hadn't done this part above, what you would have done. All right. So continuing on. A carnival game, and this should have been a 0. The carnival game allows a player a choice of simultaneously rolling 2, 4, 6, 8, or 10 fair dice. Each die has 6 faces, 1 through 6. So basically, when we roll a dice, we can get a 1, 2, 3, 4, 5, or 6. After the player rolls the dice, the numbers that appear on the faces land up are recorded. The player wins if the largest number recorded is a 1 or 2. So basically, this is the only way I win. Well, to win in this game, that's gonna happen, well, 2 times out of 6, which is 1/3. So there's a 33% chance of me winning. All right, how many dice should the player roll to maximize the chance of winning? Well, we're not just rolling 1 dice, we're rolling 2, 4, 6, or 8, or 10. So in this case, it's like, all right, I can do 1/3. This would be for 2 dice. This would be for 4 dice, 6 dice, 8 dice, and 10 dice. Well, 1 divided by 3 raised to the 2nd power, 0.111 chance. On this one, parenthesis 1 divided by 3, close parenthesis, raised to the 4th power. Ooh, it's getting smaller, 0.012. And I'm just going to skip all the way to the end because I have a feeling you know where this is going. And all of a sudden, we're getting 4 decimal places, which is approximately 0. Now, it's not. But obviously, we want to roll twice. Okay. Rolling twice gives us the best chance of winning, and we actually have a 1/9 chance, or 11.11% chance of winning. All right. Finally, last one for this video. There are 2 games involve flipping a coin. In the first game, you win a prize if you throw between 40 and 60% heads. All right. In the second game, you win if you can throw more than 75%. For each game, you'd rather flip the coin 50 times or 500 times, justify your response. Well, I'm going to assume that the coin is fair. So if the coin is fair, the probability of a win equals 1/2, 50%. Law of large numbers says the more I do it, the closer to the expected. The expected. Well, in this case, if I want it to be between 40 and 60%, well, 50% is there. And so the more I do it, the closer I'll be. So for the first game, for the 40% to 60%, law of large numbers says do it over and over and over and over again. So I want to do that one 500 times. 500 times. Well, you probably figured out that if that one is 500 times, the next one is going to be 50, and you'd be right. But here's why. 75% is not expected. Is not the expected. And since we want to be different than the expected or theoretical probability, we want to do it as few times as possible. We want to flip 50 times for the second. And once again, the reason for that is law of large numbers says if we do it over and over again, we get closer and closer to reality. Well, I want to be close to 50% because that's in between there. So if I flip it 500 times, I'm going to be even closer than I would be if I flipped it only 50 times. This says I have to be at 75%. Well, that's not what's expected. So if I'm not going to be what's expected, I want to do it as few times as possible. All right, thank you. This is the end of the first video.